All right, I'm here to talk about using SAX, the symbolic aggregate approximation, for time series anomaly detection. First question is, what is SAX? SAX is a methodology for taking a time series and reducing it to a symbol inside a fixed symbol space. A fixed string of letters that are drawn from a small alphabet. So in our examples here, we'll use a 3-letter alphabet with an 8-letter SAX word. Now, SAX was invented by Dr. Eamon Keough at the University of California at Riverside about 2002, along with his team of graduate students, and has been in the academic community quite vigorously ever since, although not many commercial applications have been found for it just yet. It allows time series to be searched and matched because it uses a symbol. You can use standard programmatic techniques to manipulate time series. Now, how do we obtain a SAX word? Well, the first thing you do is you reduce the time series to a piecewise aggregate approximation, which averages the components of the time series into a fixed number of data boxes, which will correspond to the SAX letters that we use. We then z-normalize it and divide the normal distribution into equal area sections. So we use the quantile to divide the distribution of our SAX word into the various letters that we have. So in this case, we have an example of a time series being reduced to a 3-letter alphabet, 8-component SAX word. By the way, this slide was by Jessica Lynn and Dr. Eamon Keough at the University of California at Riverside, and is used with their permission. Now, how do you find an anomaly once you have one of these things? Well, the basic idea is that each SAX word exists in a SAX space, which is a fixed size. In our example here, we have 6,561 possible SAX words. So in an even distribution of those SAX words, you would expect a 1 in 6,561 probability of a SAX word occurring. Well, they don't do that as you feed them through time series. That each SAX word is an index into that space, and I can count them. And so as I count them, I have a notion of how rare or normal a particular SAX word might be. And I can use that to compute how anomalous the situation is, because I know the total number of time series I've seen, the number of instances of a particular SAX word, and the space in which it exists, which is sufficient information to compute a p-value of how probable it is that I will have seen so few, or in other words, how anomalous a time series might have been. Now, p-value isn't the only metric that you want to compute here, or even the best one. We use it as an example because everyone knows what it is. Oh, okay. And anyways, and that's the end.